Hey there, everybody. I hope the quiz went well. This last section that we're going to talk about this week is on a totally new topic. We did antiderivatives on Monday and then finished that up on Wednesday. We talked a little bit about some summation notation, sigma notation on Wednesday in preparation for what we're going to talk about today. The topic for today is areas under curves. And it's a very different topic than what we've been dealing with up to this point. But it turns out it's related to some of the things that we've talked about before. So let me just review real quick. The idea that motivated what we were talking about way at the beginning of the course, when we were dealing with derivatives, was that we might have some function and we want to know the slope of the tangent line. And the reason we wanted to know slope of the tangent line, there were actually lots of different reasons, but slope of tangent line, which we turned out to later call derivative, is related to, it is an instantaneous rate of change. So anytime you have something changing, like your velocity is change in position or acceleration is change in velocity, you're looking at a slope, an instantaneous rate of change, so a slope of a tangent line. And the way that we got the tangent line was we used secant lines to then approximate tangent lines, right? So we used secant lines to approximate a tangent line, and the slope of that tangent line ended up giving us a derivative. And then we used derivatives in lots of different contexts, okay? So that's kind of how we ended up with derivatives. We're going to set derivatives aside for a little while. Not actually, it turns out not that long because they're related to what we're going to talk about here. But we're going to talk about a different problem that was actually plaguing mathematicians at the time too. And that is, how do I get the area under a curved surface? How do I calculate the area under a curved surface? People could calculate the areas under flat surfaces pretty easily. So for example, if it was something easy, like let's take the area, let's take the function 1 plus 2x, so that has a y-intercept of 1, and slope of 2, so I'm going to go up 2 over 1. And if I were to ask you the area under this, under f, I'll explain what I mean by that, from x equals 0 to x equals 2. What I mean by that is from 0 to 2, if I were to kind of draw straight down, the area between that function and the x-axis, if I were to say how much area was there, one way you could calculate that is by cutting it into a triangle and into a rectangle. So the rectangle here would have area, length or width 2 and height 1. So that area is 2. This triangle has width 2 and height 4. So it's going to be 1/2 base times height, so that's going to be 4. So the overall area here would be 6. But if you're dealing with a curved surface, it gets a lot more tricky. So as an example, if I were to take the function x squared, looks something like this, and ask about that from like 0 to 1, so what is the area under this function f from 0 to 1? Okay, that looks like this. Curved surfaces are much, much, much harder to find areas for. And so there were actually two clever thoughts that Newton and others had related to solving this problem. The first clever thought is that, well, finding areas of curved surfaces is really hard, but finding areas of rectangles is easy. So is there a way to use the idea of rectangles to get close to the area of this thing? Now, one way I could do that, this is kind of a silly way right now, is that I could take one rectangle with width 1 and height 1. Okay, height, what I would get if I plugged 1 into the function. If I were to take that approximation there, that's an okay approximation to the curve. It's better than taking a rectangle that's like way up here. Okay, the way that I would notate that is that this is an area approximation using the right side. So I'm going to use an R that denotes right side. And I'm using one rectangle. So I'm going to put a 1 under right to the lower right of the R. One rectangle. R1 means I'm going to approximate using one rectangle. Okay, and that approximation has width 1. So this is the width. And the height is also 1. So the overall approximation there for the area is 1. Now that's an over approximation. Okay, this is an upper approximation. So maybe a better way to do this, instead of using one rectangle, would be to use two rectangles. Okay, so in other words, if this is 0, this is a half, and this is 1, if I were to use two rectangles here, and I were to use the right sides of these intervals here, so on this interval I'm going to use the right side. Okay, and if I were to find this rectangle and this rectangle, that's going to be a better approximation than this, just using that one rectangle. Okay, now I'm using right sides with two rectangles, so I'm going to call that R2. And to get that total area, I need to add up the areas of the two rectangles that are there. Okay. So the first rectangle has width 1/2. That's the width. And then the height of that rectangle is going to be what I get when I take a half, when I take this point and plug it in this function. That's what this height is right there. And that point is a half, and the function's x squared, so I'm going to take 1/2 and plug it into x squared. That's my height right there. Okay. Plus, now let's do the next one. Let's find the width of that one. Well, the width is going to be the same. It's 1/2. But the height's going to be different. The height here is going to be what I get when I plug 1 in the function. Well, the function's x squared, so I'm just squaring 1. So this is overall going to be 1/2 times 1/4 is 1/8. Plus 1/2 times 1 is 1/2, so I get 5/8 here. 5/8 is a better approximation to the blue area than 1 is. Okay? Could we make it better? How could we make it better? We could use more rectangles, right? So we could use 3 rectangles. I'm going to draw 4 here. Okay, I could have used 3. There's nothing special here. Right, but here I'm going to use 4 rectangles. Okay, so this is going to be 1/4, 2/4, 3/4, and 4/4. All right, and I'm going to use the right sides. So I'm using right sides and 4 rectangles. And I'm going to draw, oops, that's not a great illustration here. I'm going to draw my rectangles. Okay, so those are my 4 rectangles there. So now, and you can see that that is an even better approximation than using 2 rectangles. right? Because notice I don't have that extra area that's sitting there that I had over here. So now to get this, what I'm going to do is I'm going to take each rectangle's width, so 1/4, times the height. Now the height here is what I get when I plug 1/4 into the function. Okay, next one, width times height. Height is what I get when I plug 2/4 into the function. Okay, width times height is what I get when I plug 3/4 in the function. And width times height is what I get when I plug 4/4 or 1 into the function. Okay? Does that make sense? And I could calculate that. That's going to be some number of 64ths, but it's going to be a better approximation than what this one was. Okay? So what do you think I'm probably going to do at this point? The idea that Newton had was that if instead of using 1 or 2 or 3 or 4 or 8 or 10, the more rectangles I use, the better my approximation seems to be. So why don't I figure out what the area is with n rectangles and then let n go to infinity and see what happens. It's true that rectangles are going to get super, super, super small, but there's going to be more of them. So what's going to happen? So let's answer that question. Let's try that out here. Some of you may say, let's not, but I say, let's try that out here. Okay. So what we're going to do is instead of using 1 or 2 or 4, we're going to use n of these. Okay, now n is some general thing, so we're just gonna, I'm not specifically thinking of a particular width, but I'm just gonna divide this up into n pieces. And when I do this, I'm gonna actually follow the same 4 or 5 steps, okay? First step, they're n equal pieces, so my first step is to divide the interval into n equal pieces. All right, and then I need to figure out what the width of each one of those pieces is, because we're going to use that width for the rectangles. Now we call the width delta x. If the overall width here is 1, and I'm dividing it into n pieces, then it makes sense that each piece should be 1 over n wide, right? So the width of each of those rectangles is 1 over n. All right, which means that this one right here is at 1 over n, this one right here is at 2 over n, this one right here is at 3 over n, etc. Sorry, this may be a little small. I'm just going to draw in. So my next step here is I'm going to draw rectangles using right endpoints. You don't have to use right endpoints. The book talks about upper sums, which means you use the highest point on the interval, which in this case is the right endpoint. You can also use the left endpoint. If you use the left endpoint, then we say that, we call that L sub 1 or L sub 2 or L sub 4 if you use the left side. If you use the right side, we use the term R. Okay? Usually I use right endpoints. And you can just draw in a few rectangles. You don't have to draw in them all. Okay? So now the next step is we're actually going to calculate the area of the rectangles, which is what we're calling Rn. Okay, so in our case, here, let's calculate the area of that first rectangle. So the first rectangle has width 1 over n, and the height is what I get when I plug this right endpoint into the function. Now the function's x squared. So what I get when I plug that in is 1 over n quantity squared. All right, that's that first rectangle. The next rectangle has width 1 over n, and the height is what I get when I plug this right side into the function. Now the right side is 2 over n, and so that's what I'm going to plug into the function. In other words, I'm going to square it. Okay. Then the next rectangle has width 1 over n, and it's what I get when I plug the next point into the function. That's 3 over n. And I keep going until I get to that last point, this last rectangle here, which is going to have width 1 over n. And the height is what I get when I plug this point into the function. In other words, I'm plugging 1. So I could write 1 squared. That's really n over n, kind of like this was 4 over 4. So I'm going to write that as n over n squared. Okay. Now, what I need to do, I need to calculate the area of these rectangles. I'm going to try to simplify this using some of my sigma notation ideas that we talked about last time, okay? So first of all, let's kind of clean this up a little bit. This is 1 squared over n times n squared is n cubed. Here I've got 2 squared over n cubed. Here I have 3 squared over n cubed. And then I have n squared over n cubed. I want you to notice that they all have an n cubed, so we're going to pull out that 1 over n cubed there, and we're going to get 1 squared plus 2 squared plus 3 squared all the way up to n squared. Okay? In other words, if I were to put that in sigma notation, you're kind of guessing where I'm going here. That is, you see that 1, 2, 3 all the way up to n, so I've got a sum of things that are squared, so I'm going to call that I squared. And I starts at 1 and goes up to n. Okay? That's our summation notation. If you were to pull out your sheet here, one of the things that you'll notice is that we have a formula for that. If we have the sum of squares, we actually have a nice formula for that. That turns out to be, we've got that 1 over n cubed sitting there, but the sum of squares is n times n plus 1 times 2n plus 1 over 6. Okay. So let's clean this up just a little bit. We've got n. We can cancel one of those n's there. And then on the top, we've got, if we were to multiply this out, we would get on the top 2n squared plus an n for foiling, outside and inside, plus an n and plus a 2n is plus a 3n. And then final is plus 1. And the bottom is 6n squared. So this is the formula. If you were to use 10 rectangles, then you'd plug in 10 here. If you're using 100 rectangles, this would be the formula using 100 rectangles. Okay? So that gives you any number of rectangles, that would be the area. The key thing now, the last step we're going to do, is we're going to let n go to infinity and see what happens. Okay? So if we take the limit as n goes to infinity of Rn, in other words, we're taking the limit as n goes to infinity of this thing, 2n squared plus 3n plus 1 over 6n squared. This should bring back to you the memory of, what do we do when we let n go to infinity or we let x go to infinity? If we've got a fraction here, we divide by the highest power of x, or in this case n, on the bottom. So the highest power of x on the bottom is 2, or n is 2, so we're going to divide the top and bottom by n squared. And what we're going to get here is the limit as n goes to infinity of 2n squared over n squared is 2. 3n over n squared is just 3 over n. And 1 over n squared. And then that bottom is just 6. Okay, what you'll notice here is that these two terms, just like we did when we had x's, those two terms are going to go to 0. So the limit that we're going to get here is 2 over 6, in other words, 1/3. That is this blue area right here. The area under x squared from 0 to 1 is 1/3. Or it should be if we're approximating with rectangles. Does that make sense? Kind of. So that's the idea behind what we're about to kind of embark on. What we're going to do today is just several more examples of that, and then next week on Monday we'll tackle this more kind of in depth. But for now, we just want to actually do some examples here. This is kind of like, this should remind you a little bit of like directly trying to compute limits. We're kind of in that stage right now, right? Okay. So let's take another example here. Let's take the function 1 plus 2x on the interval from 0 to 2. Okay, so a y-intercept of 1 and a slope of 2 up 1 over 1. All right. And we already know what the area here should be. I think we computed it already. I believe that the answer we got was 6. Let's try it with our rectangle method and see what happens. Now, we could do some approximations here, right? We could, for instance, use one rectangle. So if I were to do R1, in other words, one rectangle right here like this, the width of that rectangle would be 2, and the height would be what I get when I plug 2, when I plug 2 into the function. Now when I plug 2 into that function, I get 5. So that rectangle is 10 right there. We know that the answer should be 6, so this is not a great approximation, but it's okay. If I were to use 2 rectangles instead, so in other words, and use right sides, so in other words, I cut it into 2 pieces. First rectangle would look like this, and the second rectangle would look like this. And the areas of those rectangles, each of them has width 1. And the height of the first rectangle would be what I get when I plug 1 in the function. When I plug in 1, I get 3. Second rectangle has width 1, and what I get when I plug 2 into the function is 5. So I would get 3 plus 5 is 8. That's a better approximation than the one that I was using before. It's an upper approximation. It's going to be bigger, but it's a better approximation. So now the question is, why don't I just use n rectangles, do this in general, and then let n go to infinity and see what happens. So that's what we're going to do here. Okay, let me redraw this. 1, 2, 3, 1, 2. Okay. Okay, so here's my region. The first thing that I'm going to do, just like before, is I'm going to divide my interval into n equal pieces. Okay, in this case, the overall width is 2. So my width of each piece, which we're calling delta x, if I have n equal pieces and the overall width is 2, then the width of each piece is going to be 2 over n, right? The width of each piece is going to be 2 over n. Second step that I'm going to do is I'm going to draw the rectangles. And again, I'm going to use, you don't have to, but I'm going to use right endpoints. I'll talk a little bit about that using something else a little later. But I'm going to use right endpoints. So what I'm going to do is I'm going to draw in a bunch of these types of rectangles here. Okay, and I'm going to cut my interval up, and then I'm going to draw rectangles using the right sides. Okay, I don't have to draw all the rectangles, just a few of them. All right, and then I need to calculate the area of all those rectangles. And the area is going to be the total area of the rectangles. We're going to call that Rn. So what we're going to do is we're going to take the first rectangle is 2 over n wide. That's what we decided down here. And the height is going to be what we get when we plug this right point into the function. When we plug that, the right point is 2 over n here. Okay, so when I plug that into the function, what I get is 1 plus 2, and then I'm plugging in 2x, but instead of x, I'm getting 2 over n. Okay? Next rectangle is 2 over n wide, and the height is what I get when I plug this right endpoint in. Now the right endpoint, for the first endpoint I got 2 over n, the second endpoint is going to be at 4 over n. So I'm going to plug that into the function. So instead of 1 plus 2x, I'm going to get 1 plus 2 times 4 over n. Let's do another one. Next rectangle has width 2 over n. And the height is going to be what I get when I plug this point into the function. And that point is 6 over n. Okay, so I'm going to get 1 plus 2x, but instead of x, it's 6 over n. And I'm going to keep doing that until my last one is 2 over n. And the height is what I get when I plug the right endpoint in here. Now the right endpoint is 2, so it's going to be 1 plus 2 times 2. Okay. Make sense where I got all that? Those are all n of those rectangles. Now we want to clean this up some. So in order to clean it up, notice everything has a 2 over n, so let's factor out that 2 over n. And what I'm going to get is 1 plus 2 times 2 over n plus 1 plus 2 times 4 over n plus 1 plus 2 times 6 over n all the way up until I get 1 plus 2 times 2. Now, to get some pattern here, you notice I have 2 over n, 4 over n, 6 over n. The last one is 2, but it's really 2n over n. Do you see that pattern? These are even numbers at the top, 2, 4, 6. And we're going all the way up until we hit 2, but to get a pattern here so that everything looks the same, if I had an n on the bottom, I would need a 2n on the top. Now, something else I want you to notice here. I have 1, 1, 1, 1, 1, 1, 1, 1. How many 1s do I have? Well, I have n rectangles, and each of those n rectangles has a 1, so I actually have n copies of 1. Right? So I'm pulling all the 1s out and bringing those together. Everything else 2 times 2 over n, 2 times 4 over n, 2 times 6 over n, until I get 2 times 2n over n. That stuff, let's keep trying to make that a little bit simpler. I've got everything in here has a 2 over n. So let's pull out the 2 over n. And what I'm left with there is 2 plus 4 plus 6 all the way up to 2n. Do you see a pattern there? Do you see a pattern going on there? What's the pattern? What is that pattern? These are all even numbers. It's 2 times 1, 2 times 2, 2 times 3. Let's rewrite that just for a second. Two times 1, 2 times 2, 2 times 3, all the way up to 2 times n. So we could actually pull, out of this sum, we could pull a 2 out as well. Let's do that. So instead of a 2 over n, I'm going to get 4 over n. And I have 1 plus 2 plus 3 all the way up to n. Okay? So in other words, if I were to multiply this 2 over n in, I would get 2 over n times n plus 8 over n squared times this thing. All right? Fun. Now we're almost there. I know this seems like kind of crazy, but it's not too crazy. 2 over n times n is just going to give me 2. And I've got 8 over n squared times now you've got a sum of things. Those things are ranging from 1 to n. Okay, that's one of our sigma notations, one of our formulas that we had. It's actually, this is the one that Carl Friedrich Gauss figured out. Remember that? If I want to add up the numbers from 1 to n, that actually turns out to be n times n plus 1 all over 2. Okay? So let me maybe continue up here just to try to finish this off here. Rn is 2 plus, if I cancel one of these n's, I have on the top 8n plus 8, and on the bottom 2n. Okay. So if I were to use on this, for instance, 100 rectangles, the area of those 100 rectangles would be 2 plus 808 over 200. Now the last part, the sort of the last epiphany that Newton had was, let's let n go to infinity and see what happens. So if we let n go to infinity, oops. So I want to take the limit as n goes to infinity of 2 plus 8n plus 8 over 2n. Now the limit of 2 is just 2, so that 2 is just going to stay there here. But the 8n plus 8 and over 2n, I'm going to divide, since I have a fraction there, I'm going to divide the top and bottom by the highest power of n, which is on the bottom, which is n. So what I'm going to get here, I'm going to keep writing my limit, I've got a 2 there. If I divide the top by n, I'm going to get 8 plus 8 over n, and the bottom's just going to be 2. And that 8 over n part goes to 0 nicely, so the answer turns out to be 2 plus 8 over 2, which is 2 plus 4, which is 6, which actually is the number that we computed before. So you might think, well, why did we do this if we got the same number as before? But the thing that this should tell you is that doing this seems to give you the right answer. Okay, this is only one example of it giving you the right answer, but it seems to give you the right answer. Does that make sense? All right, so we're going to try one more example, and we'll try it with this same problem. We're going to do a different interval. We're going to try the same thing again. Then I'll do some summary comments, and then we'll take a look at some more examples on Monday. Okay? All right. So I'm going to try the same function, 1 plus 2x, but we're going to do it on a different interval. Okay. So instead of going from 0 to 2, I want to go from 2 to 4, and I want to show you how this is going to be a little bit different. Okay? All right. So we're going to go from 2 to 4. And we could do some initial approximations. I'm not going to do that here, just for time's sake. So the first thing, again, we're going to do is we're going to divide the interval into n equal pieces. And so the width here, which is delta x, well, the overall width is still 2. I just shifted the interval over. So that if I do n equal pieces, it's still going to be 2 over n. Okay. So then let's draw the rectangles. And let's, again, use the right. So we're going to divide this into a bunch of different pieces. And I'm going to use the right endpoints here. Okay. All right, and then my third step is to calculate the total of the areas there, right? All right, so the area of the first rectangle right here is going to have width 2 over n. And then the height is going to be what we get when we plug this point into the function. Now, the function's 1 plus 2x, so that's, I'm going to plug some point into 1 plus 2x. Now this point right here, we're starting at 2 and going over a little bit. We're going over the width of the rectangle. So the width of the rectangle is 2 over n. So that point right there is 2 plus 2 over n. That's what we're going to plug in to the function. Okay? Got it? The next rectangle is width 2 over n. And the height is going to be what we get when we plug in another point into the function. That's going to be, we're starting at 2, and instead of going over 2 over n, we're going over 2 copies of that. We're going over 4 over n. Okay. 2 plus 4 over n. The next rectangle has width 2 over n, and height, what I get when I plug the next point into the function, well, the next point is going to be 2 plus 6 over n, dot, 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 and then the last rectangle is going to be 2 over n, and what I get when I plug 4 into the function, in other words, 2 plus 2n over n. Okay? Kind of makes sense? Those are my areas of my rectangles. Okay, again, I think the thing that's a little bit kind of weird here 0, 1, 2, 3, 4. If I've divided this, just to kind of make this a little bigger, if each of these is 2 over n, this point right here is going to be 2 plus 2 over n. This one's going to be 2 plus 4 over n. This one's going to be 2 plus 6 over n, etc. That's where I'm getting those points from. And then I'm just plugging them in the function. Okay? All right, so let's clean this up now some. So everything has a 2 over n. So let's just pull that out so that we're not dealing with it. And then I've got 1 plus 2 times 2 plus 2 over n. 1 plus 2 times 2 plus 4 over n. 1 plus 2 times 2 plus 6 over n. And then all the way to 1 plus 2 times 2 plus 2n over n. Okay. So let's think about how we can clean this up some. Number one, we have a bunch of 1s again. We've got n copies of, we have n rectangles, and each one of those rectangles had a 1 showing up. So we've got n copies of 1, so let's leave that. Okay, everything else, this right here, this right here, this right here, and this right here, has a 2 on it. So let's factor that 2 out. Sorry, my laptop keeps falling asleep. Let's factor that 2 out. And then what's left there is 2 plus 2 over n, 2 plus 4 over n, 2 plus 6 over n, 2 plus 2n over n. Okay? So we've got 2 over n, n plus 2 times. Now notice I've got a bunch of 2's here. I've got n of those 2's, so let's just call that 2 times n. And then what's left over is 2 over n, 4 over n, 6 over n, all the way up to 2n over n. We're almost there. All right, so we've got 2n there. Now notice everything left over here has an n on the bottom, and on the top, everything's even. It actually, this is 2 times 1, 2 times 2, 2 times 3, all the way up to 2 times n. So I'm going to factor a 2 over n out, and here I'd be left with 1, here I'd be left with 2, here I'd be left with 3, all the way up to the last thing that I'd be left with was n. Okay. Now, the nice thing there is that we have a formula for this, right? We have a really nice formula for that. 1 plus 2 plus 3 all the way up to n. That's on your summation rules here. That turns out to be n times n plus 1 over 2. So let's fill that in and see how we can get some of this cleaned up now. We've got 2 over n times n plus 1 over 2. So let's do a little bit of cancellation here. We can cancel some 2's and one of these n's. And what we're left with is n plus 1, and here we have 2n. So 2n plus n plus 1 gives me 3n plus 1. So now if I were to multiply that 2 out in there and kind of combine some things, I've got 6n plus another n is 7n plus 2 times 1 is 2. So overall, I've got 14n plus 4 all over n. Which is actually 14n over n is just 14 plus 4 over n. So that means that if I let n, so if I was using 100 rectangles, this would add up to 14 plus 4 over 100. So now, what you'll notice is that if I, my last step here is to let n go to infinity, the limit as n goes to infinity of this is the limit as n goes to infinity of 14 plus 4 over n, but that 4 over n is going to go to 0, so the answer turns out to be 14. Make sense? All right, so in general, so let me conclude here with some ending thoughts. All right, so in general, we've got so if I have a function, f of x, on an interval from a to b, the way that I approximate the area is, so the first thing that I do is I'm going to divide that interval into n equal pieces. Now, in general, you don't have to use this formula in general, but in general, the width of this is b minus a. So if this was 5 and this was 2, the width would be 3. Okay, so the width here, again, which we call delta x, is the overall width divided by n, whatever that is. That could be 3 over n or 5 over n or something. Then I draw my rectangles. Again, you don't have to use the right endpoints. I typically do. The book will talk about if you use right endpoints, then sometimes you can see, in this case, if I use the right side, sometimes I end up with things that are smaller. Sometimes I end up with things that are bigger than the estimated area that I plan. If the book talks about upper sums, they always want you to use the bigger thing, the thing that's going to give you the biggest height. If they use lower sums, they want you to use the thing that's going to give you the smaller height. So the book isn't actually interested necessarily in using the right or left side. They're interested in using the highest or lowest points. In most problems that you're working, unless they say use upper or lower sum, you can use the right endpoint. Now, in number 24 and 26, you're going to want to be careful there. The upper and lower sums, you're going to have to figure out, if I use the left or right side, what's going to give me the highest there. But then to get the, if I calculate the area of the rectangles, the area of the rectangles is always going to be the width of each rectangle times the height, and the height is what I get. So if I were to, the height is what I get when I plug each special point into the function. Okay, so if I called this point, for instance, x1, then the height would be what I get when I plug x1 into the function. The next rectangle would have width delta x, and the height would be what I get when I plug this point. Let's just call that x2 for right now into the function. The next one would be width delta x and height, what I get when I plug x3 into the function, all the way until what I get when I plug in the last point into the function, in other words, b. So now what you're interested in doing here is collapsing this formula down into something that's nice, kind of like we got at the end here. And we may have to use your sigma notation, your formulas there. But we want to collapse this down to a point where we get some nice formula. And then the last thing that we want to do is let n go to infinity, and that's going to give us, that limit is going to give us an approximation for that area. Okay? So we're going to do more with this. Go ahead and try some of the homework problems. I will try to give you, I think, some of those homework problems, I think when you get to 47, 48, 50, 52, those I may try to give you, I may do a separate video to develop those this weekend, so that you may be able to look at those in case you need something to follow, because I know that these, especially when you're getting into this kind of stuff, the algebra can be kind of messy. So I'll try to put that together and get that out to you guys separately. Hope you have a great weekend, and we will come back and talk a little bit more about areas related to this on Monday. Thanks.